Hello everyone, this is lesson 9 of acids and bases. This is possibly the most useful and important lesson of this course, at least as far as university experiments go. Titration is used lab technique, especially for undergraduate students. It's also a very common technique if you wanted to get a job in a lab. For example, if you worked at the water quality treatment plant in Manitoba, any of them, you would likely spend much of your day doing titrations because a titration can be used to determine a lot of things, and especially used to determine the concentration of something that you don't know the concentration of. So, for example, we use it in our example, we're going to be using it to determine the concentrations of acids, but you can use the same procedure and the same technique to determine the concentration of toxins, the concentration of impurities. You could determine the concentration of heavy metals. These can all be done through the technique known as titration. So a titration is a carefully controlled reaction, in this case neutralization reaction that we're going to be doing. To perform a titration, you need some sort of standard solution. So standard solution is one that you know the concentration of. In our case, we're talking about a strong acid or a base that you know the concentration of. Often you know this concentration by using a method that is dependable. Like for sodium hydroxide, for example, you can weigh out the sodium hydroxide pellets, and they will give you, provided your sodium hydroxide sample is very clean, you can weigh out the pellets on a scale and then dissolve them very carefully in a graduated cylinder and get a very accurate solution where you know the quality of the solution up to many decimal places or many significant figures. And then with this standard solution, with a concentration you know, you can react it with a solution that you don't know. A burette is used, so this is the burette here. It has a little valve at the bottom that you rotate with your fingers as you look at your sample, which is sitting in an Erlenmeyer flask below. And so you can see it here. So this is the Erlenmeyer flask, this is the burette, and that is the stopcock that you rotate to open and close the burette and let the sample drop. And the sample will drop simply by gravity, and then along the burette there will be markings that will indicate how much base you've added. And you simply use simple subtraction to determine exactly how much of the acid or base you've added. Then you will attempt to reach an equivalency point, and at the equivalency point the sample will become neutral. And at that point the pH will switch from being basic to acidic or acidic to basic depending on what you're titrating with. And that means that this change can usually be detected using an indicator. An indicator is a chemical that changes color under different pHs, especially under a basic and an acidic pH. The equivalency point is a single point defined by the reaction stoichiometry, and the endpoint is determined by your choice of indicators. So this is where it'll depend. Some solutions that you're trying to form, you might be trying to form a solution with a very specific pH. So for example, you might be looking for a pH, you might be looking to make a solution that has a low pH, and in that case you would use a titrant, or a titration indicator that turns color at a lower pH. In our case, we almost, in many cases, you're going to use something called phenolphthalein, which is a chemical that turns pink at about a pH of 8.2. And this is very close to 7, so it's very close to the neutralization point, at least especially on a log scale. All right, so I've made up some numbers here because normally we would do this in the classroom and we would have a setup in front of us and we would have a solution with a given molarity. And I'm actually gonna change this molarity because I don't think I would want to work with 1 molar sodium hydroxide if I can help it. So let's just work with 0.15 molar sodium hydroxide, and we're going to take a 20 ml sample of acid. So we don't know the concentration. The concentration of this acid is unknown, and we've put it in a flask, and we're going to start adding sodium hydroxide to it. So we add some sodium hydroxide to it, and we go until the sample changes color, until the end point happens. And let's imagine that this 20 mils takes 35 mils of base to change color. Okay, what does that mean? So what we want to be able to do is take this value. So now we have a volume of a base that we used, and we want to know how many, and our end result is what is the concentration of the acid. Well, a concentration of an acid would be the number of moles of that acid divided by the volume of that acid. This 20 mils will be that volume eventually, but we don't know how many moles there are. But by the same token, we do know the concentration of our base, and we know the concentration of a base times the volume of a base would be equal to the moles of that base. Now if you are able to determine the moles of a base, since you have this value here, and way up here we have our Cb value, then you have the moles of the base, and at the equivalency point, NB should be equal to Na, right, at pH 7. So if we hit that color change right on the dot, then the number of base will be equal to the number of acid, and then we can work towards determining what is the concentration of acid. That will be our end goal. So that's how this sort of works. We have a standard solution that we know the concentration of, and we use it to determine unknown concentration. Okay, so let's think about what we have. So we have, I sometimes think about it as like a base side and a acid side. And I believe this is what we did in an earlier unit, or an earlier lesson. We have an acid and a base side. We have a concentration of our base, which we said was going to be 0.15 molar. And we have a volume of a base, which was, did I say 35 milliliters? Okay, so that's 0.035 liters. And so together, this would be giving us a number of bases, and our base here is sodium hydroxide. And so by multiplying these two together, we are going to get, let's see, 0.15 times 0.035. We get 0.00525, and that is the number of moles of sodium hydroxide. Well, luckily, sodium hydroxide reacts with the acid in a 1-to-1 ratio. So whatever our number of moles of sodium hydroxide are, we have the same number of moles of acid, whatever acid this is. Now we have to think that our original solution we were originally reacting with our solution that had a volume of only 0.025 liters. And so we want to use those two together, divide them, and get our concentration of our acid. So 0.00525 divided by 0.025, and we get a concentration of 0.21 molar. And we could even figure out the pH if we wanted. We could even figure out the pH if we wanted, because we do have that 0.2. So there you go. That's what we're going to do, and that's all we needed to do for that one. Now I want to look at this next example because it's really interesting. So I guess we kind of skipped ahead here, but this is going to be our solution there. So whatever this acid is, it's relatively acidic. So sometimes the sample being tested is in the solid form. Since we can determine the number of moles of an acid or a base, we can determine the mass or molar mass of an unknown solid sample. And this is where it becomes very useful for environmental techniques. Environmental techniques, you've got some amount of iron dissolved in a sample of rainwater, but you don't know how much. If you can titrate it, if you can find the right kind of chemical that will react with it, and it will cause maybe a change in pH, so you can use an indicator, then you can titrate out the iron concentration and figure out how much is there, or how much of whatever it is, whatever toxin or whatever you're interested in. Okay, so for this next question, we have quite a few steps to take care of. We have a student who's receiving a solid sample of sulfamic acid, which is a monoprotic acid, and he's dissolving the sample in enough water to make this solution. So we do get a volume, an original volume of our solution, but we're actually going to care about the aliquot first. So the sulfamic acid has a molar mass. We're going to use that later. The student takes a volume of 12.00 mils, or 0.01200 liters of that acid, and they titrate it with a base that has a concentration here of 0.0985 molarity, and of sodium hydroxide. This is NaOH. So, and over here we're going to do our acid, sulfamic acid. Okay, and the sodium hydroxide. If 13.38, so the base is 13.38, oops, again in liters, not in milliliters, so 0.01338 liters of the base is needed to reach the endpoint. What is the mass of the sample? So first things first, how many moles of base did you use? So we're going to do some multiplication there. So 0.001338 times 0.0985. So we used up 0.000131793 moles. In this case, we have quite a bit of significant figures, so we should keep as much as we can for now until we don't need it. It was monoproduct, so that means that we can keep it we can make them equal. So this is the number of acids, and so that acid concentration is going to be the same. Okay, and then I want to figure out that concentration of the acid, so I'm going to divide these two, moles over volume. So I'm going to divide this by the 0.01200 liters. Okay, so this is the concentration of the acid, and I guess we have 4 significant figures, so we'll leave it there. So that is the concentration of acid. So the question is, how much is the mass of the sample of acid? And that sample was dissolved in 100 milliliters. So this is where it gets tricky, where you have to keep track of how much of everything. Where did you get this? This is all related to the aliquot, right? This is related to the titration. So that's the titration. Titration, not sample, let's call this aliquot. And now we're going to talk about the sample. So the sample is, the sample has a volume of 0.1000 liters. That's this one up here. And we now know the concentration of that sample, which is 0.01098. And so that means that the moles of that sample are going to be simply multiplying CV equals N. So I'm going to take this answer here. I'm going to multiply that by that volume, 0.1. So that means that I have 0.001 0.098 moles. And now, if that's how many moles I have, now I can finally use that molar mass. So that molar mass is going to be grams divided by moles. So again, actually, I can go, I'm going to put that molar mass down here just because I'm running out of page here. Grams per mole. And I can kind of follow the same trend. It's because I'm going the same way. If I multiply again, taking n times molar mass will give me the mass. So I'm going to take that answer again, and I'm going to multiply this by 97.09, and I'm going to get 0.1066 grams. And that's my final answer. So that student, or whoever it was, yeah, it was a student, they must have received 0.1 grams of this sample. And in this way, they could possibly, with a very good titration setup, not have to worry about massing anything. They could actually figure out their masses by titration instead of using a scale. Is that easier than using a scale? Well, probably not. Now, if you were very careful and were able to, especially with a pH meter, you could actually measure the pH throughout this titration process. So as you're adding the base to the sample, you could measure a pH. So here we have an example where we have 25 mils of hydrochloric acid, and we're adding some base to it. And notice that the base, that even though you're adding base, because the base is instantly neutralized, and the hydrochloric acid has a very low pH, the amount of hydrochloric acid will actually change very slowly due to the equilibrium effects. So every time that you add some sodium hydroxide, you do encounter this reaction, but the water solution and the Kw of water and that equilibrium also come into effect, and the pH actually changes very slowly at that low end. And then suddenly, and when you do this, it's almost magical. You'll drop one drop, it'll be clear, another drop, it'll be clear, and then another drop, it'll be pink, and then another drop, it'll be dark pink, and that'll be it. So drop by drop, this distance here is usually only a couple of micromils, or maybe a mil. So it's very, very difficult to manage that endpoint very carefully. It takes a lot of skill to be able to drop one drop at a time when you get right to the edge of this endpoint. So the equivalency point is found in the center of the steepest point of the curve, or when the curve appears to change directions. The equivalency volume at 25 mils of 0.1 molar NaOH, since the base is 1:1, would be at a equivalency point of 0.100 moles per liter. Okay, so the pink on the graph indicates the color change of phenolphthalein with pH change. Despite the color change at a higher pH than equivalence, the difference is not significant because the curve is so steep at the equivalency point. So that's why we can still use phenolphthalein, is that as long as you're dealing with strong acids and strong bases, this curve changes so rapidly in this very narrow window that even though the pH changes a little bit high and the equivalency point is a little tiny bit low, the actual amount of distance in this direction is so minuscule that your result will not be different if you take the value here or if you take the value here. That will still be within the error of the measurement for your equivalency point. So there's some practice here. I worked this practice out for my previous class, so you can see some examples of how this might work. Because the equivalency point is so hard to work with sometimes, you actually have to do this experiment more than once. So a sample of vinegar is titrated with 0.99 molar sodium hydroxide. The following data is collected. Here's your final burette reading. So this is the number remember that the burette is organized in this direction. with a wheel on the side here. And so the numbers will go from, so the initial reading would be something like this, so it's 0.24, and then the final reading will be this 11.87. And then the difference between these two is going to be this value, and that's the volume used. And you can see that that value, you can take the difference between the initial and the final to find your total volume every time. And you can see the trials using the acid or using the base. Okay. And I guess they titrated out a certain amount of acid. So for example, for this first titration, there is 11.63 milliliters of base used and 13.86 milliliters of acid. The second trial was 6 and 7 and 9 and 11. So it makes sense. They kind of follow each other fairly closely. And then what they ask is to calculate the concentration of acetic acid in vinegar for each trial. So for each trial, we had to calculate out the concentration, the volume of the base, the volume of the acid, the concentration of the base, the concentration of the acid, by using an equivalency. And one way of doing that is another equation you can use, which is that the concentration of the base should be times the concentration of the volume of the base should be equal to the concentration of the acid times the volume of the acid in the case of monoprotic acid. So you don't even have to go to the point where you determine the number of moles. You can simply solve this equation. So you can see how that would work here. Why don't we work out the equation number 2? Let's do trial 2 together since we have this worked out. So trial 2, we have a volume of base, which is 6.45. We have a volume of acid, which is 7.68. We do know the concentration is 0.9990. So that's the concentration of the base equals 0.990. And so what is the concentration of the acid? That's the question. Maybe let's do a little rearrangement so we can kind of play with it in the same space we did before. So the way we've been doing it was to organize it this way, and so that they were kind of parallel to each other. I think sometimes we put concentration below, that's fine. And then we put the N up here, just because I like to be really clear. Base, acid. So we would take the concentration of a base, 0.990, times the concentration of the volume of the base, which is in milliliters actually. So I was being really lazy last year apparently. Not even changing to liters. 0.06385. This will become the concentration of the number of moles of acid. And then to determine the concentration, we simply take this number and divide it by our volume of acid. And that gives us our final value of 0.83 molar. Again, and so that's where that number comes from. And you can do that, repeat that again with the last one. And you can calculate the average. The average turns out to be 0.83, of course, because all three of them worked out to 0.83. And then if we wanted, we could even take it one step further. We could even determine the pH using the assumption that this is a monoprotic acid, acetic acid, so it is. And we could even work out some other details here, like the Ka value, it looks like. Okay, well, yeah, this is interesting because it is a, well, that's okay. I obviously went an extra step there with the Ka. So try out some of these other ones. I might post yet another video going through a couple more of these problems, maybe tomorrow. And in the meantime, good luck, and we will talk to you in the next video.